A water skier is being pulled by a tow rope attached to a boat. As the driver pushes the throttle forward, the skier accelerates. A 70.3 kilogram water skier has an initial speed of 6.10 meters per second. Later, the speed increases to 11.3 meters per second. Determine the work done by the net external force acting on the skier. Okay, so to solve this problem, first we needed to know that the net work is equal to the kinetic energy final minus initial kinetic energy. And then we know that the formulas for kinetic energy is equal to 1/2 the mass times the velocity squared. So the first part of the equation uses the final velocity, and the second part of the equation uses the initial velocity. So when we look at the problem, we know that 70.3 is the mass of both, 11.3 is the final velocity, and 6.10 is the initial velocity. So we plug them into the equation, and we get that work is equal to 4,488.3 minus 1,307.4. And when we solve this, we get our final answer that work is equal to 3,180.37 joules. The hammer throw is a track and field event in which a 7.3 kilogram ball starting from rest is whirled around in a circle several times and released. It then moves upward on the familiar curving path of projectile motion. In one throw, the hammer is given a speed of 29 meters per second. For comparison, a .22 caliber bullet has a mass of 2.6 grams and starting from rest exits the barrel of a gun at a speed of 410 meters per second. Determine the work done to launch the motion of A, the hammer, and B, the bullet. So, since we are given the mass and the velocity for both the hammer and the bullet, we're going to use the formula that net work is equal to kinetic energy. And kinetic energy is the same as 1/2 mv squared. So, work equals 1/2 mv squared. And for part A, we know that 7.3 kilograms is the mass and 29 meters per second is the velocity. So, when we plug the values into the formula, we know that work equals 1/2 7.3 times 29 squared. If we multiply this together, we get the result that work equals 3,069.65 joules. And that would be our answer for part A. Now for part B, we are going to use the same formula since we are also given the mass and the velocity. The only thing is that they change because now we're going to determine the work done to launch the motion of the bullet instead of the hammer. So now we know that our mass is 2.6 grams. And we cannot have it in grams since we need it in kilograms. So we use dimensional analysis as shown here to get the answer that 0.0026 kilograms is our mass. And we know that 410 meters per second is the velocity. So we plug the values into the formula and we get that work equals 1/2 0.0026, which is the mass, times 410, which is the velocity, and that is squared. So when we multiply this together, we get that the work is equal to 218.53 joules, and that is our final answer for part B. It takes 185 kilojoules of work to accelerate a car from 23 meters per second to 28 meters per second. What is the car's mass? So since we are given the velocities and we are given the work and we need to find the mass, then we can use the formula that net work is equal to the final kinetic energy minus the initial kinetic energy. And we know that our work is 185 kilojoules, but we need to convert this to joules, so we use dimensional analysis. And once we do that, we get that our work is going to be equal to 185,000 joules. So we know that 28 meters per second is our final velocity and 23 meters per second is our initial velocity. So now we plug the values into the formula. We know that our work, which is 185,000, is equal to 1/2 the mass, which we do not know yet, but we are going to solve for, times the final velocity squared, which is 28 squared, minus 1/2 the mass, times the velocity initial, which is 23 squared. So now we get that 185,000 is equal to 392 mass minus 264.5 mass. And then when we solve for mass, we are going to get that our mass is going to be equal to 1,450.98 kilograms. And that is going to be the final answer. An asteroid is moving along a straight line. A force acts along the displacement of the asteroid and slows it down. The asteroid has a mass of 4.5 times 10 to the 4th kilograms, and the force causes its speed to change from 7,100 to 5,500 meters per second. What is the work done by the force? And if the asteroid slows down over a distance of 1.8 times 10 to the 6 meters, determine the magnitude of the force. So for part A, we can use the formula that net work is equal to the final kinetic energy minus the initial kinetic energy. And if we look back at the problem, we know that our mass is 4.5 times 10 to the 4th kilograms. The initial velocity is 7,100 and the final velocity is 5,500. So when we plug the values into the formula, we get that work is equal to one half the mass, which is 4.5 times 10 to the 4th, times the final velocity, which is 5,500 squared, minus 1/2 the mass, which is the same 4.5 times 10 to the 4th, times the velocity initial, which is 7,100 squared. Now when we solve this, we get that work equals 6.81 times 10 to the 11th minus 1.13 times 10 to the 12th. And that would give us our final answer, which is that work equals negative 4.5 times 10 to the 11 joules. So that's the answer for part A. Now for part B, they are asking for the force. And we know the work, and then the problem they give us the displacement. So we would use the formula for work equals force times displacement. So we know that the work is negative 4.5 times 10 to the 11 joules, and we know that the displacement is 1.8 times 10 to the 6. So using these values, we can solve for force, and we get our final answer, which is that force equals negative 2.5 times 10 to the 8th newtons.